Welcome back. In this lecture, we will look at oxidant utilization in a fuel cell. The typical oxidant in a fuel cell is just oxygen. Oxidant is one which gets reduced while oxidizing something else, right? Oxygen is getting reduced during the operation of fuel cell. It will lead to H2O, which may be in the vapor phase or as a liquid product, depending upon the type of fuel cell. U indicates utilization. The utilization of O2 is given by this formula, rate of oxygen consumption divided by rate of oxygen supplied. Oxygen consumption is current density times area, total active area available in the fuel cell, divided by NF. N is 4 here in this context. Because for 1 mole of O2, 4 moles of electrons are consumed to reduce oxygen. In the denominator, we have the mass flow rate of air because oxygen is not supplied in the form of pure oxygen, but is supplied in the form of air because it's much less expensive to supply air instead of pure oxygen. Then the mole fraction of oxygen divided by the molecular weight of air. This gives you the moles of air that is being supplied. So let us do a thought experiment to think through the trade-off associated with oxidant consumption. So some mechanical energy is utilized for pumping the air through a fuel cell. So you may imagine that you will want to supply very limited amount of air so that the pumping costs can be reduced and all the air that is being supplied is utilized by the fuel cell. Let us think through this way of thinking by imagining a thought experiment. So air is coming in, it is being utilized, and the unutilized air is let out in this direction. So you imagine that this electrode is divided into 3 particular components. This area, and this area. And imagine in this thought experiment, this area is not connected to this area and is not connected to this area. This is just a thought experiment to convey a point. So in this area, closer to input of air, there is a lot of air available to you. So even though you increase your current density, the concentration over potential does not kick in. That is, you have greater limiting current density in this area because of greater amount of air being available. So this is a polarization curve. This region is dominated by activation over potential. This is the ohmic over potential region. Because of very limited amount of oxidant available to you at higher current density, concentration over potential kicks in. Therefore, the potential that you can get from the fuel cell dramatically decreases in this region. You do not want to be operating in this region. So air continues into this region. So as some of the air has been utilized in this region, the amount of air available to you in this region is less. And in this thought experiment, you are trying to obtain the polarization curve for this region alone, in a way independent of current from this region and current from this region. As you increase the current density, at a current density lesser than the current density here, the concentration over potential region kicks in. So here, the limiting current density was about 35 ampere per meter squared. But here, it is about 22 ampere per meter squared because the amount of oxygen available to you, to the fuel cell in this region is lesser because some amount of oxygen has already been utilized in this region. So continuing the thought experiment, you have a region of the electrode that is electrically disconnected from these two regions, but it is connected in terms of airflow. Much of oxygen has been utilized in this region and in this region. So the amount of oxygen that is available to you is lesser. Therefore, you will get limiting current density sooner because you have overall less oxygen that is available to you in this region. So the activation over potential kicks in, or the transport over potential region kicks in at a lesser current density because the overall amount of oxygen available to you is lesser in this region. So remember that why there is activation over potential or transport over potential is that the amount of O2 available near the electrode surface is lesser, and at limiting current density, the concentration is close to zero. A very, very limited amount of oxygen is available in as you get to limiting current density. So you do not want to be operating in these regions because in this region, the O potential losses are significant. So this points to the trade-off that is involved in oxidant utilization. If you consume too much oxygen, that is, if your oxygen utilization is very high, you may have regions in the fuel cell where you are under activation or transport over potential region, which you want to avoid. So if you utilize, so in the next slide, we will look at something, some additional point. So here you may imagine this four curves to illustrate four different conditions. So if you do not, if your oxygen utilization is very less, that is, if you do not use much of oxygen, your utilization is very less. So there is no region in the fuel cell electrode which is under activation over potential region. So your cell potential is always high. So even at very high current density, you are not in the activation over potential region. So this corresponds to very less utilization of oxygen. But what is the problem? Even though your over potential loss is very limited, you would be spending a lot of energy in pumping a lot of oxygen or air through the fuel cell, and much of the air is not utilized. As opposed to that, this is another extreme between these four curves, wherein the utilization rate is 50%. Therefore, the current density you can obtain is lesser, and at a lesser current density, you are automatically in the activation over potential or transport over potential region. So here, your potential losses are greater. You do not want to be operating in any of these regions. So a good design point to be operating is at a point where no parts of the fuel cell electrode is in the activation over potential region. So you do not want to be utilizing too much of oxygen because some parts of the electrode surface will have very little oxygen, and those parts of electrode surface will be in the activation or in the concentration or transport over potential region where the potential losses are significant. So this indicates such a point where the activation or transport over potential has kicked in. So in this region, you typically are under ohmic overpotential region. So this is a good point to operate. So in this point, the utilization is moderate. At very low utilization, your cell potential might be very high, but the amount of oxygen that is being transported is very high, and much of the oxygen is unutilized. So you'll be spending a lot in pumping a lot of air, and your current density will also be lesser, even though your potential is greater. In this region, your utilization is high, therefore your pumping costs might be lesser and your current density might be higher, but your cell potential might be lesser. So as I've mentioned a few times in this course, all of engineering or much of engineering is about trade-off. If you gain some, you may lose some other aspect. So you have to choose an optimal operating point or a design point wherein your utilization is reasonable, your potential losses is not too much, and current density is also reasonable. In the next lecture, we will look at fuel utilization. Thank you.